So, welcome back to the course on architectural design of IC. So, in the last class we have seen what is the meaning of, or what is this constant multiplication, and then why I require this reconfigurable architecture for this constant multiplier design. What is the usefulness of constant multiplier design? That means in compared to the generic multiplier of design, I can save or I can optimize the multiplier design in a better way whenever we are doing this constant multiplication operation. Okay. So, after that we have considered one 3 type FIR filter where we are using 3 constant numbers, which is let us consider A, B and C. So, at the time after that we have seen that okay, it requires this 24 number of ANDing operation, then 21 number of addition operation to do this whole of to implement the whole circuit of doing this AX in, BX in and CX in. Okay. So, now my point is that can I optimize this more, or this can I save or can I reduce these numbers 24 and 21 in a better way, or in a, that means can I reduce this number? If I can reduce, then how can I reduce that? So, I told you that for that there are different algorithms to do that. Okay. So, among them this binary common subexpression elimination algorithm is one of the efficient one, which can by which we can reduce, which is basically applicable for reconfigurable this constant multiplier design, by which we can reduce this number. So, how we can reduce this number, that we will see. So, suppose in a constant multiplication operation, okay, we are having this input and the coefficient. So, input and the coefficient means x in is the input and coefficient is the nothing but this A, B and C. So, each of these, if I consider, each of these are of 16 bit. Okay. So, 16 bit means if this input is x1, okay, they are of 16 bit, and this y1 is basically A into x1, okay. Means what? This y1 is basically A into x1, okay, equals to y1. So, how can I write this y1? I can write considering the fact that what I said, that the worst case condition of this A is when all the bit position of A are 1. When all the bit position of A are 1, at that time, that means each of this product term I have to consider, right. Means what? Means what? At that time, that means A 15 into x1 by 2 plus A 14 into x1 by 4, A 13 into x1 by 8, something like this, each of this bit, if each of this bit is 1. So, that means at that time this equation can be written only in terms of x1, and that is basically written in this form, where I have removed the corresponding A position, considering that A 15 is 1. So, I will get x1 by 2 here, A 14 is 1. So, I will get x1 by 4 here, A 13 is 1. So, I will get x1 by 8 over here. So, A 12 is 1. So, x1 by 16 is 1. So, in this manner I will get, that means for the doing this A x1 which is y1. So, I will get each of the terms which I have to add. Okay. So, in here what is there, that means we have considered 16 numbers. Let us consider 8 numbers. Okay. So, if I consider 8 numbers, so A into x1 which is y1, that can be written as x1 by 2 plus x1 by 4 plus x1 by 8 x1 by 16 plus x1 by 32 x1 by 64 x1 by 128 plus x1 by 256, right. Now, if you see in these particular terms, each of these basically contains the values of x1. So, now if I take this as a common term, actually this is nothing but actually this is generic mathematics. If I take this x1 plus 2, x1 by 2 plus x1 by 4 as, let us consider this as x2. Okay. So, now how I can represent the same equation? So, this now this can be represented as x2. So, if I just take 1 by 4 common over here, so this can also be written as x1 by 2 plus x1 by 4. Then if I just take common of this, so this also can be written as x1 by 2 plus x1 by 4 plus again here if I take common, so x1 by 2 plus x1 by 4, right. So, if I just take this x1 by 2 plus x1 by 4 as x2, so how can I write x2 plus this is also x2. So, now it will become x2 by 4 plus here x2 by 16 plus x2 by 64. Okay. That means, now what I have to do? Initially only once I have to do this x1 plus 2 x1 by 2 plus x1 by 4. That means, if I just do it x1 by 2 and x1 by 4, this is producing x2, right. So, then to do this what I require? Then this basically again it will come, this is basically right shift by 4 means this is by 2 bit. So, I need another addition operation where this is 16 means this is basically left shift by 4, then again I need to do this where this is basically left shift by 6. And then if I just add, then finally I will get the same thing, the whatever is the, that means this y1 a into x1, the same thing I will get by this corresponding structure. If I take common of this x1 by 2 plus x1 by 4. That means, now initially if I do not take common, so at that time how many addition operation I require? That is 7 numbers, right. In this particular case, if I take common as this x1 by 2 plus x1 by 4 as x2, if I take it common, the factor as common. So, then how many require? 1, 2, 3, 4. So, that means 4 number of addition operation I require now. So, that means the number now becomes down to 7 to 4. So, for one particular multiplier, now this number has come down to 4. So, for 3 how many require? 12 number of addition operation, whereas initially it was 7 into 3 21 number of addition operation. So, that means now I can save 9 number of addition operation. Okay. So, these particular things whatever I did, that x1 by 2 plus x1 by 4 which I have take it common. Okay. So, this particular things is basically known as binary common sub expression elimination algorithm. So, these are the basically sub expression which is related to this. So, based on that now I can reduce the number of addition terms in this way. Okay. So, this kind of structure is basically useful, very much useful whenever we do this reconfigurable constant multiplier design. So, that means now what is that, for one constant multiplier I am saving 3 number of addition operation. So, now more the number of constant multiplication is required for one filter implementation or for any transfer implementation. So, the more number of constant of this I will use, more the number of savings I can guarantee. That means, for 3 numbers that becomes 3 into 3, 9 number savings. So, if the number is 10, so that means at that time the savings will be 10 into 3 is, that is 30 number of addition operation. So, the more in the number of that constant multiplier, more in the number of saving. Okay. So, this is the fact that using this binary common sub expression, this is the beauty of this binary common sub expression algorithm, which is basically used for constant multiplication operation. Okay. So, if you just, and here you see application, it can be used in any digital filter, then any transform which is basically FFT, DWT, DCT, DHT, and as you see that this constant multiplication that can be represented in terms of, that can be done in terms of binary common sub expression, then canonical sign digit based common sub expression, then this residual number system based common sub expression, then canonical sign digit based expression, all the things you can do. Okay. So, here what is this consider, this is basically considering this 2-bit binary common sub expression. So, why 2-bit? As this x1 by 2 plus x1 by 4 if I take. So, at that time here actually it is taking x1 a plus x1 by 2. So, instead that you can also take x1 by 2 plus x1 by 4, nothing is actually, that is not a problem. It depends upon which common sub expression you want to basically take it common. Okay. So, as we are considering only 2 numbers over here. So, that is why 2 number means that they are basically differed by their positions. So, this is 2 to the power minus 1 position, this is for 2 to the power minus 2 position. Okay. So, that is why we are considering 2-bit binary common sub expression. So, if we take common 3 number of them, that means x1 by 2 plus x1 by 4 plus x1 by 8. So, at that time it becomes 3-bit binary common sub expression. So, if you take it 4 terms common, that means it becomes 4-bit common sub expression and elimination algorithm. Okay. So, it depends upon that how many number of bits you want to take it common for this binary common sub expression. Okay. So, it is not that the more the number of that means common sub expression you will choose, if the length of this BCS is more, that means that this number, the number in the later case, that will be reduced by divide of that. Divide of that means here you see, as I am considering 2-bit. So, that means this 16 numbers that has reduced to 8 now. Okay. So, if I take it common 4 terms over here, so at that time it will become 4, the 4 terms will come over here. Okay. So, that means 4, for doing this 4 I need 3 adder, and here to doing this then again I need another 3 adder. So, total 6 number of addition operation I require at that time. Initially here I require to do this 16, I require 15, but if I take 14-bit common, sorry 4-bit BCS, so at that time 6 number of addition operation I require. So, if I take 2 bit BCS common, so at that time for this I need 1 and 7 I will get over here. So, total 8 number of addition operation I require. So, that means the more the number of bit you consider for BCS, the lesser the addition operation you require to do this constant multiplication. But the fact is that at that time the addition operation, which I am not considering in this particular fact, actually if I just see the corresponding structure of this. Okay. So, this is basically this for this x1 plus x1 plus x1 by 2 that has been generated through this partial product unit, and based on that in each of this addition operation is basically doing this. Okay. If I take 4 bit common, so at that time for doing this x1 plus x1 by 2 I need only one adder, right. But if I take 4 bit common, so at that time how many bits I need to do add? How many bits I need to add? So, at that time I need to add x1 plus x1 by 2 plus x1 by 4 plus x1 by 8. That means, at this I need 3 adder in a chain. Okay. So, 3 adder, and then again this particular this will be then added in a chain. So, then again for this another 4 bit that means 4 of this addition operation x1 by 2 plus x1 by 4 plus x1 by 8 plus x1 by 16, this requires another 3 level of addition operation. Sorry, not 3 level, this requires basically 2 level of addition operation. So, that means total 4 level of addition operation I require. So, that means it is not the fact that more the number of BCS I will choose, okay, and I will get the benefit in terms of the area will be minimized at that time, the number of addition operation will be minimized, but the speed wise the addition operation in a chain that will be maximized at that time. Okay. So, that is why it is not that you need to choose this size of the BCS in such a way, so that you are getting in terms of this speed as well as the area. In both the things, if you are getting the benefit, so at that time you choose the BCS according to that. Okay. So, according to that we have seen that this 2 bit BCS or 3 bit BCS, they are the like the max, that means they are the most useful BCS terms, or the length of the BCS is more, that means the advantageous one in terms of speed as well as the power and area for constant multiplication, this reconfigurable constant multiplication design. Okay. So, this is one of the technique used for this constant multiplication. Now, again you see another thing over here. How can I now, what is happening? Now, the thing is that I require total what I said, that means for this I require 12 number of addition operation, right. So, can I reduce this number more? Can I reduce it? Yes, I can reduce it. How can I reduce it? Then again actually if I just write these particular terms, a into x1, that is x1 by 2 plus x1 by 4 plus x1 by 8, x1 by 16, okay. So, what I did initially, x1 by 2 plus x1 by 4 plus 1 by 4 x 1 by 2 plus x 1 by 4 1 by 16, that is x 1 by 2 plus x 1 by 4, then again 1 by 64, that is x 1 by 2 plus x 1 by 4, right. So, what I did, x 1 by 2 plus x 1 by 4, I write that as a x 2. So, this will become x 2 plus x 2 by 4, then x 2 plus x 2 by 16 plus x 2 by 64. So, in the next level, if you see these corresponding terms, x 2 plus x 2 by 4, if you take common, then x 2 plus x 2 by 4, that means what? X 2 plus x 2 by 4, if I take that as a x 3, so this can be written as x 3 plus x 3 by 16. So, that means to do this x 2 plus x 2 by 4, I require what? I require only one adder. Here I require one adder, and to do this x 2 plus x 1 by 2 plus x 1 by 4, I require one adder. So, that means total 3 number of adder operation I require to do this whole addition operation. Here I require how much? I require total 4 number of. So, that means here if I take another level common, so that means at that time I require only 3 number of addition operation. So, that means now initially how many? I require 21 number of addition operation, right. That is for unoptimized case. So, after doing this 2 bit BCSE, okay, so the number becomes 21. Then again if I take 2 level of common, so at that time it requires 3 into 3 means 9 number of addition operation. So, the same, this is 2 bit BCSE, but the common I have applied on 2 directional, which is vertical ones and horizontal ones. Okay. So, how vertical ones, how horizontal ones, that I will show you in the that means presentation, but here the number will become 9 now. So, initially we have started with 21 number of addition operations. So, after 2 bit BCS we have found out the number as 12. So, after that we have come down to the number as 9. So, that means total how many numbers? 12 number of addition operation we are saving for these 3 particular things. So, that means the more the number of that means constant multiplier we use, more the savings we can guarantee for using this binary common sub expression for constant multiplication operation. Okay. So, this is the beauty of this particular algorithm and this particular method. Okay. So, here you see this is the that means this 2 dimensional factor. So, here if I consider this 4 coefficients, suppose I consider. So, and the length of this is 16 bit, length of the coefficient if that is 16 bit. So, 3 bit will be applied like this, as this you see. So, H 15, H 14, H 13, this will be applied something this. If I have to use this 2 bit BCS, so at that time it will consider only 2 consecutive bits, that means which is H 15, H 14, H 13, H 12, H 11, H 10, H 9, H 8, something like this. So, instead 3 bit it will consider 3 consecutive bit, which is H 15, H 14, H 13. Okay. So, considering this fact, I will get the circuit something like this. The architecture for this is for one single constant multiplication. Okay. Then for this is for 3 bit one single constant multiplication. Then as what I said, this basically suffers from the, that means if I consider another level of optimization. Okay. So, at that time I can reduce the number more. That means here what we do, that means initially we did the, that means initially what happens at the very first level, considering this 2 bit, we have applied the common sub expression once. Then what we did, this among this, that means here you see which direction I am basically applying this corresponding this common sub expression, that is in the vertical direction. Okay. Now, this among these horizontal direction, that means between each of these coefficient, if I have to find out another common sub expression. So, at that time I can reduce the number more by another 1 if I consider this 8 bit coefficient. Okay. So, that we have already seen in the previous case, and based on that we can come down to this another architecture. That means, here this will basically skip the multiplication operation. The multiplication operations are there, but if I found that more number of common, so at that time that particular multiplier will be used, skipped, it will use the shifted version of the previous results. Okay. Means what? Actually what we see here, from here what we have seen, that after doing this taking common of this x 1, we are getting this x 2. Then again we are taking common of this x 2 terms to get the terms reduced by only 2. Okay. So, that when we will get the terms common in terms of x 2, then only I can come down to this x 3 terms. Okay. So, in this way we are basically doing the optimization in the reconfigurable constant multiplier design. Okay. So, this is just to using the binary common sub expression. So, if you can use any other number method instead of binary, you can use this residual number system, and then you can apply this common sub expression elimination to get the results more, or you can use this canonical sign digit based format number representation, and then you can apply this common sub expression to reduce the number in a more way. So, that means this is the way of doing the, or this is a techniques, that means step by step technique how we can reduce the number, the number of this addition operation in a better way. Okay. So, this is the end of this multiplier chapter. Okay. So, from tomorrow we will or from the next class onwards we will start to see about this different architecture or different, that means structure for doing this. That means, now we have built up the basic operation like adder design, we have gone through the multiplier design, we have gone through the basic this algorithms part, we have already gone through that. That means that 2x, then 2x plus 1, then 4x, then log 2 base x. So, that kind of simple block structure, efficient way to design that we have already done. Operator wise we have already designed or we have learned the facts. Now, based on these particular operators, now we can design the functions. Okay. Now, we will try to see the architecture of function which are basically used different of these operators. So, that means, now what this function level architecture, now I will try to optimize, and in this function level basically architecture, they require this operator level architecture. So, operator level architecture optimization we have already seen. Now, function level optimization we will see. So, that means there will be two-way optimization level. Okay. So, from the next class onwards we will try to see different architecture of function like FFT, first Fourier transforms, then this codic architecture. Okay. So, what for they have used and what are the architectures available for, and how you can develop the architecture for that we will see from the next class onwards. So, thank you for today.